In 1957, at an observatory on the outskirts of Puebla, Mexico, someone held a photographic plate up to the light. It was a study of faint blue stars, discrete objects, almost all white dwarfs, far from the plane of the Milky Way. Nothing that seemed extraordinary at first glance. Among those points, one stood out, not for its shape, but for its color. On the plates taken with the 0.7-meter Schmidt telescope of the Tonantzintla Observatory, it appeared decidedly violet. It was not a poetic nuance. It was a technical fact. That hue implied an anomalous emission toward the blue, something that did not quite fit with an ordinary white dwarf. Astronomers Braulio Iriarte and Enrique Chavira noted it in their catalog. Another entry in a long list: Tonantzintla 618, Ton 618. At that moment, that code meant nothing more than a position and an unusual color. No one was talking yet about supermassive black holes, not even quasars. TON 618 remained there, a violet point on a Mexican plate, a data point in a catalog, an object that no one suspected would, decades later, be considered one of the largest monsters in the observable universe. The next step in its story came far from Mexico. In 1970, a radio telescope in Italy detected an intense radio source at the same position. That blue star turned out to be radio bright. That was a clear sign. It was not an ordinary star, it was an active nucleus, a quasar. Shortly after, more detailed optical spectra were obtained. The light from Ton 618 showed emission lines extremely redshifted. The pattern was unmistakable. A very distant object, moving at high speed due to the expansion of the universe. The redshift, Z approximately 2.2, implied an enormous distance. What was seen in those spectra did not belong to the galactic neighborhood. We were looking at a bright nucleus, located billions of light years away. When apparent brightness and distance were combined, the conclusion was direct and astonishing. To appear that luminous from so far away, TON 618 had to be releasing an absurd amount of energy, much more than any entire galaxy like ours. The estimated value of its luminosity is around 140 trillion times that of the Sun. It is one of the brightest beacons in the entire observable universe. That brightness does not come from a swarm of stars. It comes from a single nucleus, a supermassive black hole surrounded by a disk of gas falling into it. Friction, turbulence, and magnetic fields convert gravitational energy into radiation. The result is a quasar, a point that, in a photo, looks like a modest star, but in physical terms, eclipses hundreds of billions of suns. Distance adds another layer of strangeness. The light from TN 618 has traveled about 10.8 billion years before reaching our telescopes. That means we see it as it was when the universe was only a quarter of its current age, about 3 billion years after the Big Bang. We are not observing a black hole as it is now, but an ancient phase in the life of its host galaxy. To be so bright, and above all to host a black hole of the size we now infer, on the order of 66 billion solar masses, according to the most widespread estimates, Ton 618 had to grow very quickly. It had to accumulate mass at an extreme rate, in a universe that was still organizing its first large structures. In the simplest models, a continuously feeding black hole, limited by the pressure of its own brightness, the Eddington limit, needs a long time to reach such gigantic masses. Too long if starting from small seeds. TON 618 forces one to question whether our assumptions about how these objects grow are incomplete. Perhaps there were much larger initial seeds, or brief phases of uncontrolled accretion above the classical limit, or repeated mergers between already enormous black holes. Seen from Earth, all of that reduces to a point. A point in an image of the sky taken with a medium-sized telescope. An object seemingly accessible to advanced amateur observation. From an observatory in a desert or on a mountain, TON 618 does not impress visually. It is just a faint star. The contrast between that modesty in the image and the actual scale of what lies behind it is perhaps the most unsettling of all. A feeding black hole does not look like an isolated dark pit. It looks more like an overflowing power plant. We do not see the hole itself. We see the fate of everything that falls into it. Gas, dust, torn apart stars, remnants of collisions. Let us imagine the galaxy hosting TON 618, a structure of billions of stars, clouds of gas, dark matter. At the center, the gravitational field is strongest. The surrounding gas loses energy, falls toward the nucleus, and accumulates. But it does not fall in a straight line. It arrives with spin, with angular momentum. That forces it to form a disk. That disk is the visible heart of the quasar. A thick ring of gas spinning at relativistic speeds around the black hole. Each layer of that gas brushes against the next. There is friction, turbulence, collisions. The gravitational energy the gas loses as it falls is converted into heat. The result is a plasma at extreme temperatures, capable of emitting from radio waves to X-rays. In the case of TON 618, this machine is pushed to the limit. Its total luminosity is on the order of tens of trillions of times that of the Sun. No ordinary combination of stars produces anything like this. The only mechanism that fits is violent accretion onto a supermassive black hole. In simple terms, matter falling toward the center converts mass into energy, with an efficiency far greater than the nuclear fusion inside a star. From the outside, the appearance of that nucleus would be radically different from that of a quiet galaxy. If we could get close enough without being destroyed by the radiation, we would see a blinding point at the center, a beacon surpassing the combined brightness of all the other stars in the galaxy. The spiral structure, the arms, the halo, would be submerged in a glow emerging from the accretion disk around TON 618. That brightness is not smooth. The disk is not a perfect ring. There are instabilities, denser regions, magnetic fields twisting and reconnecting, zones where gas accelerates and slows down. Each of these irregularities leaves traces in the light spectrum. Broad lines, shifted, widened by enormous velocities. These lines are one of the keys. By measuring their shape and width, one can estimate how fast the gas is moving, and from there, the mass of the black hole governing it. In TON 618, these lines are extreme. They indicate gas orbiting at a significant fraction of the speed of light. At those speeds, light curves and spectral profiles begin to show relativistic effects, broadening, asymmetries, small differences between approaching and receding material. The light that reaches us has already been processed by gravity and motion. We do not see pure colors. We see photons that have been stretched, compressed, deflected. All this occurs under the pressure of the quasar's own brightness. There is a physical limit to the luminosity a black hole can reach while feeding steadily, the so-called Eddington limit. When the radiation flux is too intense, the light exerts an outward pressure on the gas, attempting to fall inward. If the radiation pressure equals the gravitational pull, accretion slows. The system self-regulates. TON 618 operates very close to that limit, or even above it in some models. That means the accretion disk is not a delicate, thin object as depicted in textbook diagrams. It is thick, turbulent, pierced by winds and jets. The photons escaping from there have had to overcome an extremely dense radiation field, a sea of charged particles and strong magnetic fields. In the innermost regions, near the event horizon, gas completes orbits in minutes or hours. Just above that boundary, any small change in density or magnetic field translates into a flash, a rapid variation in brightness. On such extreme scales, the disk is not a static object, it is a surface that boils. If we could observe TON 618 up close, with an impossible zoom, we would see layers. In the outer regions, the disk emits primarily in ultraviolet and visible light. Further inward, the temperature rises and X-ray emission dominates. Even deeper in, photons begin to lose the battle against gravity. Some trajectories curve so much that light rays orbit multiple times before escaping. Or they never escape. Above and below the disk, magnetic fields can launch relativistic jets, columns of accelerated plasma that escape the immediate environment of the black hole and extend thousands of light years into intergalactic space. Not all quasars show clear jets, but when they do, they carry a significant fraction of the system's energy. In an object with the mass of TON 618, these jets would be true spears of matter and radiation piercing the host galaxy's environment. From our perspective, all that detail reduces to a spectrum and a saturated point in an image. We do not see the disk as a resolved ring. We do not see the horizon. What we can reconstruct is the general structure, a gigantic black hole surrounded by an accretion disk that converts infalling matter into a colossal emission, capable of outshining the entire galaxy. That is the visual paradox of active black holes. The most defining part of their structure, the event horizon, is the only part we never see. It is hidden not behind something, but behind space-time itself. What dominates our observations is not the whole, but the immediate periphery, the zone where gas can still scream before disappearing. Current estimates place its black hole in a huge range, between about 40 and over 60 billion solar masses. Many popular sources cite around 66 billion solar masses. In any case, there is no gentle way to put it. It is one of the most massive objects we have identified in the entire observable universe. Mass dictates the size of the event horizon. For a non-rotating black hole, the Schwarzschild radius grows directly with mass. The Sun, if it collapsed into a black hole, would have a horizon about 3 kilometers in radius. Sagittarius. A star at the center of our galaxy has a horizon of just a fraction of an astronomical unit, roughly the size of Mercury's orbit. In TON 618, that same formula leads to a different regime. The Schwarzschild radius is about 1,300 astronomical units. That means the horizon's diameter is around 2,600 astronomical units. Put more crudely, TON 618's point of no return sphere is about 40 times larger than the size of the solar system measured out to Neptune's orbit. 1 astronomical unit is the average distance between Earth and the Sun. Light takes 8 minutes to travel from the Sun to our planet. To cross the horizon of TON 618 from side to side, a light beam would need weeks. That is the scale we are dealing with here. Not a black hole swallowing isolated planets, but a black hole capable of enclosing dozens of copies of our star's entire neighborhood within its invisible boundary. Another way to look at it is by comparing it with other famous black holes. Sagittarius. A star has about 4 million solar masses. M87 star, at the center of the elliptical galaxy in Virgo, is around 6.5 billion. TON 618, in its most extreme version, surpasses all of that in a category some call ultramassive. Black holes whose mass rivals entire galaxies in terms of stars. Imagine the solar system as a faint disk, with Neptune's orbit marking the edge. Now, superimpose that image onto the surface of Ton 618's horizon. Neptune would orbit well inside the boundary. Pluto, too. The Kuiper belt would vanish without a trace. The cloud of comets surrounding the Sun would be compressed into an indistinguishable region within that volume. We could place up to 40 copies of that drawing side by side and still remain within the horizon. Mass reinforces the impression. The central black hole of Ton 618, even if we stick to conservative estimates, has more mass than all the stars in the Milky Way combined. Our galaxy hosts on the order of 100 billion stars. If we replaced each of them with a sun, the result would still be less massive than this single black hole. And yet, on a cosmic scale, T618 is not a grotesque outlier. It is a data point, one among several. We know of other black holes nearby in mass, perhaps slightly smaller, perhaps comparable. The mere fact that they exist forces us to admit that the cosmos has efficient mechanisms to concentrate all that material into a single gravitational point. These mechanisms are long, noisy, violent. They include galaxy mergers, flows of cold gas falling from the cosmic environment, phases of unbridled accretion. But the end result, seen from the outside, is silent. A sphere of nothing defined solely by its radius and mass. There is another aspect of scale that is not apparent in the numbers, but that weighs heavily. The more massive the black hole, the smoother, in a sense, the entry to its horizon. The average density required to produce a horizon of that size decreases with mass. A stellar mass black hole is compact, brutal, almost inhuman. One of 60 billion solar masses occupies so much space that locally, the curvature at the horizon itself may be less extreme. But that nuance offers no comfort. What defines its presence is not density, but the absolute fact that within that radius, nothing can escape. From 10.8 billion light-years away, all of this contracts to a point. In deep sky images, TON 618 does not appear as a resolvable disk. We do not see its horizon, nor its accretion disk, nor its gigantic Lyman Alpha Nebula, which we now know extends beyond the host galaxy itself. We see a saturated pixel, a point object in a catalog, a code. The enormous point of no return is reduced to a flash entering the same pixel as a distant star. That discrepancy between physical reality and representation is perhaps the core of the unease. We know from simple calculations that Ton 618's horizon could engulf our solar system 40 times over. We know its mass exceeds that of many galaxies in terms of stars. We know light would take weeks to cross its shadow. And all of that condenses, in practice, into the reading of a line in a table. Estimated mass, tens of billions of solar masses. Schwarzschild radius, approximately 1,300 astronomical units. Luminosity calculations for Ton 618 place it around 10 to the power of 14 times the brightness of the Sun. It is a round approximate figure, but sufficient for what matters. We are facing one of the most luminous quasars known in the entire observable universe. A single-point source emitting as much energy as thousands of normal galaxies combined. In theory, there is nothing special about the mechanism. We have seen it before. Gas falling toward the black hole, accretion disk, friction, magnetic fields, radiation. What is extraordinary is the volume. the amount of matter that, at a particular moment in cosmic history, is being channeled into the nucleus of that galaxy and converted into light. From our perspective, the consequence is brutal. Ton 618's host galaxy is submerged under the quasar's glow. The stars, the disk, the arms, the halo, all exist, but are overshadowed by their own center. At distances of billions of light years, the telescope only records a point. The active nucleus has decisively won the internal brightness competition. This is not an absolute rarity. It is the nature of quasars in general. A quasar is, almost by definition, a nucleus so active that it dominates the total luminosity of its galaxy. But Ton 618 takes that condition to the extreme. If we imagine a galaxy with hundreds of billions of stars, the sum of all that light does not match the accretion disk spinning around its central black hole. There are not many intuitive ways to describe that. It is a galaxy whose center has taken control of the sky. That luminous dominance has profound physical consequences. Radiation is not a neutral spectacle. It strikes the galaxy's gas, heats it, ionizes it, pushes it outward. Models of active nuclei show galaxy-scale winds driven by radiation pressure, streams of gas shooting out from the quasar's environment, dragging along matter that might otherwise have formed new stars. In other words, the quasar phase can stifle the future of its own galaxy. The nucleus feeds on gas, shines enormously, and in doing so, expels and reheats the material on which future generations of stars depend. Ton 618 not only illuminates its surroundings, it reshapes them. It is a phase of regulatory violence in the life of a galaxy. On larger scales, that luminosity turns the quasar into a cosmic lighthouse. The light from Ton 618 travels over 10 billion years before reaching us. Along that journey, the universe expands. Wavelengths stretch. The spectrum shifts toward the red. And yet, the nucleus remains visible. It can be included in catalogs of bright quasars. Its redshift, broad lines, and energy can be measured. Its light traverses a large portion of cosmic history and still has enough strength to trigger modern detectors. If the brightness were a little lower, Ton 618 would be invisible to us. The expansion of space, intergalactic dust, and the limitations of our telescopes would silence it. But the combination of mass, accretion rate, and cosmic epoch places it precisely in the range where it can be detected from a corner of an ordinary spiral galaxy, billions of years later. That is another layer of the story. We see it because during a relatively brief interval of its life, it was extraordinarily prodigal with energy. This prodigality is not eternal. Quasars are phases, not permanent states. To shine like this, the central black hole needs a reservoir of dense gas continuously falling into it. That reservoir is usually associated with galaxy mergers, streams of matter converging on the nucleus, or instabilities in the galactic disk. When the available gas is depleted or expelled, the quasar switches off. The black hole remains with the mass it has accumulated, but enters a low-activity stage. It becomes more like what we see today in most galaxies, a dark, barely active nucleus like that of the Milky Way. This means that TON 618, as we see it, is a snapshot of a specific era, a phase of peak brightness. We do not know how long that peak lasted. We do not know whether, a few 100 million years after the moment we observe, the quasar was still active, or if the galaxy had entered a quieter state. All we have is the light reaching us now, a slice of the past. The magnitude of the brightness raises another technical question: how this luminosity fits within the limits imposed by physics. In theory, the Eddington limit marks the boundary between a stable accretion flow and one in which radiation pressure expels the gas. Many models suggest that quasars like TON 618 operate near that limit. Others go further and imagine brief phases above it, where accretion becomes super Eddington, at least locally, in certain regions of the disk. Whatever the exact detail, the observable result is the same: a nucleus that, for practical purposes, dominates its galaxy. If TON 618 were much closer, the sky of any world orbiting a star in that galaxy would be dominated by a fixed, intensely bright presence in the direction of the center. A constant beacon, brighter than any other object in the sky. It would not be a distant decoration. It would be a background condition, a climate of radiation. From here, from the extreme distance at which we are, all that impact reduces to a scientific advantage. Thanks to its brightness, we can study a black hole living in a much younger universe. We can measure its mass, its luminosity, its spectrum, and use it as a test for our models of galactic growth and evolution. TON 618 is at once a local phenomenon of an ancient galaxy and a tool for understanding the entire cosmos. There is something even more unsettling than the size and brightness of TON 618. It is its age, not the age of the black hole itself, which we cannot measure directly, but the age of the universe when that light left it. TON 618's redshift tells us that we see it as it was about 10.8 billion years ago. The universe was just over 3 billion years old. On a cosmic scale, that is extremely early. The first massive galaxies were barely consolidating. Many stars were still second or third generation, and yet there was already a black hole whose mass, according to our best estimates, reached tens of billions of solar masses. The contrast is stark. On one hand, a young universe that has barely had time to organize its large-scale structure. On the other, a black hole representing the extreme of gravitational growth. It is like finding a millennial tree in a newly planted forest. In the simplest models, supermassive black holes are born from small seeds, remnants of the first massive stars. Corpses of a few dozen or 100 solar masses that begin to slowly accrete gas. As they feed, they grow. But they cannot do so at any rate. If they shine too brightly, the radiation pushes outward the gas trying to fall in. That balance defines the Eddington limit. And under that limit, growth is slow in cosmological terms. There is an approximate rule often used. The mass doubling time of a black hole accreting continuously near the Eddington limit is on the order of hundreds of millions of years. If you start with a seed of 100 solar masses and double it, and then double it again, you need a long chain of stages to reach 1 billion, then 10 billion and beyond. The cosmic clock does not always allow enough time, especially if the process is interrupted or slowed. TON 618 seems to defy that orderly story. We see it so large, so early, that the numbers do not comfortably add up. It is not the only case. There are other massive black holes detected in high redshift quasars that present the same tension. But TON 618 is among the most extreme. It is, so to speak, a stress test for our theories of formation and growth. To accommodate objects like this, models have had to become more flexible. One possibility is that the initial seeds were not small. Instead of being stellar remnants, they could have been black holes, formed by the direct collapse of massive primordial gas clouds. Under certain conditions, low metallicity, limited cooling, absence of fragmentation, a gas cloud can avoid forming many small stars, and instead collapse almost entirely into a single object of tens or hundreds of thousands of solar masses. Starting from such a seed, the path to billions of solar masses is less demanding. It still requires episodes of intense accretion and mergers, but the starting point is closer to the goal. Even so, a great deal of growth must be compressed into a few billion years. Another option is to relax, at least temporarily, the Eddington limit. The classical formulation assumes symmetry, ordered flow, certain ideal conditions. In practice, gas can fall in streams, clumps, or dense structures that, for short intervals, exceed the average allowed luminosity. This is super Eddington accretion. It does not last forever, but it can accelerate growth during key phases. Mergers also play a role. The early universe was denser, with galaxies closer together. Galaxy mergers were a common process. Each time two galaxies with central black holes merge, their holes eventually meet. When they collide, they produce an even more massive black hole. If a region of the universe experiences a chain of rapid mergers, the central mass can grow in jumps, not just by continuously accreting gas. TON 618 could be the result of a combination of these paths. A very large seed formed by direct collapse, episodes of intense accretion, several mergers in a gas-rich environment. There is no single proven recipe. What is clear is that objects like this force us to expand the repertoire. If the model cannot produce them, the model must be revised. There is another nuance worth noting. We do not know what TON 618 is like today. We only know what it was when it emitted the light we now see. More than 10 billion years have passed since then. In that time, the black hole could have continued growing, could have depleted the gas in its surroundings and ended its quasar phase, could have been affected by new mergers or changes in its galaxy structure. It could be today an enormous but silent nucleus, invisible to our telescopes in optical light, hidden within an aged galaxy. Or it could still be active. That part of the story remains unknown.